Hello and welcome back to Statistics. Today, we will talk about something very different from the t-tests. We will talk about association analysis, basically correlation, regression, and the graphic representation, the scatter plot, the scatter and the line of best fit on this scatter, the regression line. So let's start by the very, very easy example within correlation to let's justify the concept of association by a simple example, deterministic or functional relationships. If you take a car which travels at 80 miles per hour, how far will it go in 3 hours? Simple, we can calculate, right? You just simply multiply 80 by 3 and conclude it will go all the way to 240 miles in 3 hours. There's the point where it will lead to. This is an exact linear relationship. There's no scatter around the dots. The dots will be put on a single line. You can exactly predict from X the Y value. Now, in behavioral studies, especially psychology, relationships are not deterministics. Learn and you will get better grades, or you will get along in life, right? So this is not an exact linear relationship, but there is a trend. We can kind of feel that. So also the noise or scatter is there, and we will check this out based on a very concrete example. We take a statistical measure, the so-called Pearson correlation coefficient, Pearson R, to measure the extent to which extent are these two variables related. What is the strength of their relationship? So when we talk about correlation, it means there is some connection, association. The taller people tend to be heavier. Usually the increase of one variable pulling the other increase in the other variable will result in a positive correlation, not usually, always. But you can also have negative correlations. A good example might be the higher you climb a mountain, the colder you will feel, the colder it gets. It is also possible, and let's not rule out this possibility whenever we do these kinds of association analysis. Sometimes there's simply no correlation. A good example might be, okay, you drank an amount of tea, but the level of intelligence has nothing to do with it. Let's now see if you're a good guesser. Okay, first, please guess. I'm going to show you some relationships, and you can guess whether this relationship is deterministic or statistical, non-deterministics. And also you can guess the direction of the relationship. So, question number 1, alcohol and blood alcohol content. It's non-deterministic, it's statistical, because people are different in how they consume alcohol, how they deal with alcohol in their biological system. And it's a positive relationship. Definitely the more alcohol you drink, the higher your blood alcohol level will be. How about this one? A typical deterministic relationship, and again positive. The more you apply the weight, the more the amount of stretch will be bigger. Depression and productivity is a typical negative but statistical relationship. The more depressed you are, the less productive you will be. Driving speed and gas consumed is a tricky one because it can be it is basically deterministics once you are talking about a single car with single features, but the more you step on the gas, the more gas will be consumed, but this might differ for different brands of cars or based on the age of the car, etc., etc. What else? The vital lung and of course, if you're applying different strings, then this deterministics will always also become statistical. So lung capacity and smoking, statistical and negative. The more you smoke, the less capacity you will have in your lungs. Aggression and impulsivity is a typical positive statistical relationship. Aggressive people seem to be usually are more impulsive, and the more you do exercise, the less body weight you will have. So as we can see, most of our examples taken from the field of psychology are non-deterministic. Let's now turn to the association and its graphic representation, what we call the scatterplot. We take a very simple example. The more hours you study, the better your grades will be. See Peter, for example. He studied only 1 hour and got 2.3 as an average of grades. On the contrary, for example, Shelley studied 9 hours per week and she got a 5. But Kathy studied even more. How come she got a little bit less, not a 5.0 on average? Well, this happens. This is the non-deterministic feature of this relationship, and you can see the scatters. The points do not fit on a single line, but they mingle around that line, which we call the line of best fit or the regression line. We will get back to how this line is created, usually by statistical programs. It would be very difficult to calculate this line by hand. So please conclude this relationship. We can see a trend, we see a relationship, and it's positive. And now comes the human sentence, which is very important in concluding the results. The more hours they spend studying, the better their average grades are. But the direction might not always be positive. You can see here typical result from a reaction time study, and the less frequent these words are, the more reaction time is needed to name them in a picture naming task. Okay? The other side is the more frequent these words are, the less time you need them to name. Typical negative regression line, although the relationship is not very strong here. Okay, how about the correlation coefficient, this single number between 0 and +1 or 0 and -1, based on whether we're talking about a positive or a negative relationship. So we've learned 3 properties of this correlation coefficient so far: the direction, positive or negative, magnitude. If it's 1, then it's a linear relationship. If it's 0, there's no relationship. And the third property that we need is the level of significance, basically reflecting the error. We talked about significance before. This is a very similar hypothesis testing based value, and reflects how sure you can be of your decision based on the relationship estimate. Okay, let's now guess. Again, a little guessing game. I know it's not easy, but just pick a number from 0 to 1 or from 0 to -1. Is it a positive relationship? Yes, of course. So it will be 0.3-ish, definitely not 1. Oh, it's much more. 0.699 is the correct answer. Okay, how about this? Okay, then this is the 3-ish, but it's negative, right? Okay, so the regression line or the line of best fit seems to be like this, not like this. It's not the best line. Okay, and this is almost a linear trend. It might be deterministic, but not so. This point kind of gets a little bit out of the deterministic line. So plus 0.997. It's a very, very strong relationship. Also, the significance is a good question. It's very important, although you will never have to actually calculate the level of significance here. It's a very simple task to do. Once you have a certain R value, you can check, for example, in a table, or ask a statistical program to do it for you, whether for that number of elements, this strength of the relationship is significant or not. Okay, so the number of elements, the sample size count a lot. So and you also have to pre-select your level of significance. Usually we stick to this 0.05, the 5% error. So if we stick to this column, and we know that how many points do I have? 1, 2, 3, 4, 5, 6. The degree of freedom is 5. I simply stay at this vertical line and I say, oh, there's my critical value. So this R has to be larger than 0.755 in order to be significant at this pre-chosen level of significance, the 5% error. So is R equals 0.699 significant for this sample size? No, because it's lower than our selected critical value here. How about this one? No, it's definitely negative doesn't count. So it would be, if it would be negative 0.756, it would be significant regardless of the plus or minus sign. But it's lower than this value in absolute value, and thus it's not significant. How about our last example? Yes, this is a significant correlation value at both the 0.5 level and also the 0.1 level here. Okay, so let's make a quick round, okay? Again, we pre-chose our level of significance. Now, look what I did here. I simply raised the number of elements from 6 to 60. Okay, so the degree of freedom is now not 5, but 59. 59 is here. Okay, you don't see an exact value, you just choose which is closer to it. Now the 60 is closer, so 0.025 is our critical value. Is this significant? Yes. Is this significant? 0.25? Yes, definitely. And the 0.9 is significant. Question: do people marry their own IQ range? Plan a study to test this problem. Stop the video and, just put together a little case variable matrix, some variables to check. First question is, will you use a dependent or an independent sample? This is a very important step. And whenever you do correlation analysis, you need paired or dependent samples. That's the criteria for correlation. For example, you can have data for the wives, data for the husbands on IQ, and you can simply draw a relationship or not, if there's non-existent one. The variables have to be quantitative. And good news is here the scales are the same because they're both IQs, but you can have hours and grades on the two axes. It doesn't matter if the scales are different. Okay, let's now practice a little bit. Try to draw a scatter plot. Remember, we had hours and grades. You can put on the axis IQ of wives and IQ of husbands, and simply find the Rockies, the truths, etc., etc. So here will be the people, and do you see a relationship? It's difficult because you could place a line like this, you could place a line like this, and to be honest, I don't see a trend. My conclusion is that there's no linear trend here, but you could also conclude a positive trend or a negative trend, okay? If this were an exam question, there would be no bad answers because it's so messy. It's not easy to solve by hand. Your guess could be any of these three. Bottom line is that the IQ of the husband cannot be really predicted from the IQ of their wives. And if you were to put this in a statistical program, it wouldn't give you two lines. I'm just demonstrating, some guesses of how the lines fit. It would give you a positive line, but the result would be a non-significant relationship, okay? If it's non-significant, we don't report it. We simply say we couldn't see any relationship between IQ of the wives and husbands. People don't seem to marry their own IQ range. And in this case, you don't have to report any statistical values. You just simply make this conclusion. Okay, problem. Draw a scatter plot and conclude SPSS results. The SPSS results is this. R equals 0.835 and P equals 0.039. So this is a significant and positive relationship. About what? Well, TV watching habits of wives and husbands. Unlike IQ, these seems to be correlated. The more TV the husband watches, the more TV the wife will watch, with him or without him, but we see a positive trend. The correlation coefficient is large because it is close to 1, and significant. Look at the p-value. So this is the way to conclude this typical exam question. You don't have to draw a line. I'm just putting it there for you to see that it's a positive trend. Okay, what are the limitations of correlation or association analysis in general? A very good example of this limitation is the breakfast theory. The more eating breakfast in general is correlated with success of elementary school children, not because they eat breakfast, because probably there's a background variable, a good family background, or parents who look after their breakfast and their homework. So basically it's not the breakfast causing the school success, it's a third variable in the background. Another good example, when it's summer, the hardness of the asphalt correlates with the number of people fainting. Now, of course, it's not the gases from the asphalt that make people faint. There's a third variable. Can anybody guess what it is that makes both effect happen? It's the sun, right? It makes the asphalt soft and it makes people faint, and the mechanism of the effect is totally different. So remember this when you're talking about the limitations of association analysis. There's no causation, okay? This is just a relationship, nothing more. No more, no less. Homework. Plan a correlation study. You could perform with your fellow students and specify these. Don't forget units of observation, variables, hypothesis. In your hypothesis, you simply can talk about a positive or negative relationship that you expect. You can collect the data if you'd like and graph and conclude the results. Also, another exam question. Here's a result from SPSS. Draw the scatter plot. It's a very important skill to be able to draw these scatter plots and conclude results. You would conclude a linear relationship between these two, and don't forget how many samples you've seen. You can also include you have to include in your conclusion, but it's written here, the strength of the relationship in terms of the correlation coefficient and its level of significance. Okay, now we can turn to this other problem, because once there is an association, a relationship between two variables, you can always make guesses, predictions, and that's where this regression comes in. The regression equations simply determining this line of best fit. So, what is the line of best fit for these hours of studying and results in grades? Well, this is the line, and our prediction is that if I spend, based on this data, and if I'm around these students in IQ and other important matters, then if I spend, look at here, 10 hours of studying, my grade average will be 4.2. Yeah, that's good. Okay, so this kind of prediction is what our line of best fit is good for. This exact point, which is on the line, we see that the other points are not on the line, but when we're making predictions, we're talking about the line. Okay? So what is regression? Let's conclude now. This is a simple mathematical or statistical rule for a linear association between dependent variables. The rule is simple. It's the predicted value equals something plus something times what we know. Okay, this is the predictor. Determining the line of best fit is done by statistical programs, but it's important to understand how the program does it. It simply calculates the differences. Look at here. These are the sort of how far these points, either up or down from the line. It takes a squared sum of these differences, and it plays around with the lines until it finds the line of best fit where these summed squared differences are the lowest. That's the easiest way to explain this, and we are not going into the detail of how this line is calculated. But it's important to understand that the A here is the intercept, okay? It's where the predicted value of epsilon at this axis, where the other axis is 0, so this line crosses the epsilon axis. So 2.742 in this case. Okay, that's where my cursor is standing. Now B, on the other hand, is the slope of this, the angle of the regression line. For example, 0.143. Okay, but these are just numbers, but it's important to understand that this is the intercept and this is the slope. Okay, so what is regression? It's a rule of the linear association between dependent variables, but, and this is a very important but, whereas in correlation, remember I told you, you can put on the x or the y-axis whatever variable you want from the two. Here, when we're doing regression, you have a direction, a one-way street, okay? And you don't go the other way within that prediction. So you have a predictor, a designated predictor variable. We call it the independent variable, or that's the x, okay, which we want to know, which we use to predict. Then we have the y, which we want to know, that's our predicted variable or the dependent one. You can do it the other way around, but in one analysis, one calculation, you can just go one way. So the A and B are determined by the statistical program, and you will get a regression equation determining the line of best fit for each problem. So if you switch up the predictors, you get a different regression equation. You will try that in SPSS or JASP when you're doing this at the practical. So we already talked about A and B. And for example, let's see an example, because that's the easiest way to understand it. What will be my average grade if I study 1 hour in each day of the week, thus 7 hours a week? So now my predictor variable is the 1 hour or the 7 hours per week, that's the x, and I want to know the grade. I don't know the grade. We've seen that with 10 hours I get a 4.2, so for 7 hours it will be a little bit less. Let's see, 3.8 or something like that. Oh, I'm a very good guesser, because this is the regression equation for this problem. Remember, it's direction specific. And if I use it with the 7, I get a 3.74. Okay, direction, as we said, is a one-way street, okay? What if I study 1 hour on each day of the week? Okay, I study 7 hours. Then what will be my grade? That was our problem for before. Okay, here we have the two numbers, the A and the B. Okay, always in this order. We have had the x, so the statistical program will give you these numbers, but you do have to do this regression equation. You do have to calculate that 2.742 plus times 7 equals, and this will be your result for this problem. Okay, what if I go the other way around? I don't want a 3.74, I want to get a 4. I know I will have to study more than 7 hours, but what number exactly? For this, I cannot use this regression equation and these numbers, okay? I have to re-enter the problem, because now I'm going the other way. It's another one-way street. I will get a different regression equation if my predictor is the 4, okay? And my predicted value is the hours. Now I want to know how many hours do I have to study. So I get different numbers from the statistical program, no problem. I enter these numbers, and don't be afraid, it's a negative number, it's totally okay. And another number times the 4, because I want to get a 4. And thus I have to study 8.55 hours. Okay, so that's the exact amount I have to study. Of course, if it's a perfect linear relationship, in reality, I will also have some scatter, and it might not be an exact result, but the prediction tells me that I have to study this much. I hope this is clear. Limitation of the regression analysis is exactly the same as it was with the breakfast theory in correlation. A good example might be that the speed of the windmill rotation is correlated with the strength of the wind, but you cannot use the speed of the windmill rotation data to estimate the strength of the wind. Yes, you can assume, you can have a prediction here, but you cannot assume that the windmill activity is the one that actually caused this speed. Okay, so even though you can make perfect predictions, you cannot assume a causation. That's the bottom line. Okay, remember this breakfast theory. Further examples are very interesting sometimes. Okay, so a simple summary of what we've learned. Basically, the correlation coefficient and all its attributes, it has 3. And the linear regression equation, don't forget this is very important when you want to actually use the statistical outcomes, the regression determinants, the constant and the slope here, to make a prediction. Thank you very much for watching.